Okay, good morning. Welcome to the makeup class of PHYS111B. Now, in our previous lecture, we have already introduced about sound waves. Sound wave is a longitudinal wave, and we actually have derived the wave equation for sound wave. And we found that the velocity of sound wave is equal to square root of the bulk modulus divided by the air density. So this is what we found in the previous lecture. Now we are going to discuss about standing waves. Suppose there is a tube, and we set up some vibration inside the tube, and so that means there's the air molecule vibrates as a standing wave, and so there will be a standing wave established inside the tube. Now this is called sound. This is a kind of sound resonance. Now before discussing about sound resonance inside a tube, let us have a brief review of a string. Okay, when we discuss about transverse wave, we take the example of a string, and we discuss about standing wave forming on a string, right? So let's have a brief review on that. Now let's go back to this slide. Okay, now this is a standing wave pattern that exists on the string that is tied to the tied at both ends. So the two ends are fixed, and we use this standing wave solution to match with the boundary condition, right? This is what we have done in the previous lecture. And to match the boundary condition on both sides, this side I call x equal to 0. The other side I call x equal to L. To match this boundary condition, I choose the sine function for x. Okay, so I choose a sine kx. The boundary condition for x equal to 0 is automatically satisfied because when I put x equal to 0, the sign is a 0. Okay, so it's always undisturbed here. But the boundary condition at x equal to L can be satisfied only if the factor sine KL is 0. And that imposes a condition on K. K could not be arbitrary now because now I require this size to have a 0 disturbance always. And so that imposes a condition on K. I require KL is equal to n pi, or K is equal to n pi over L, right? Where n is an integer, okay? A non-zero integer, okay? So the lambda, the wavelength will then be essentially the reciprocal of K. And multiplied by 2 pi, and so that is 2L over n. And so these are the wave pattern that exists on the string, depending on n. This is n equal to 1, n equal to 2, and n equal to 3. So this gives you the relationship between the wavelength and the length of the string. Okay, so this is very intuitive when you look at the figure. In the first figure, you have the wavelength equal to half, trace the length of the string. When n equal to 2, you have the wavelength equal to the length of the string. And for n equal to 3, you have the length of the string equal to 1.5 wavelength, so on and so forth. So these are the relationship described by this formula. Okay, and this formula, you notice that is derived from the boundary condition. We impose a boundary condition that's at L, x equal to L, the disturbance is always 0. Okay, now let's take a look at the video. There's a video in Chinese, in Cantonese. I filmed with a publishing company earlier. And so I would like to share with you because it's a very good demonstration of a standing waves. Now the video is in Cantonese, but that doesn't matter. You look at the pattern, you should be able to understand it. Okay.
但唔知大家有冇見過駐波 standing wave 咧？我呢度有一條繩喎，咁呢邊咧聚咗啲重嘢嘅，所以燈行咗嘅。另外一邊咧，我駁咗個震盪器。咁而家咧，我試下用某個頻率咧嚟震盪呢條繩喎。我而家嘅頻率咧係21.5個 Hertz。咁我開始啦。
Now this is a
大家見
fundamental
到咧
frequency,
出現咗一個好得意嘅 pattern 啦。
almost
中
standing
間
wave
嘅震
pattern.
盪咧係最大嘅。
It's anti-loop in the
咁其實
middle.
咧我哋就叫做波幅。咁咧兩邊咧個震盪咧係最少嘅喎。咁呢兩邊咧我哋叫波折。咁究竟咧我如果加大個頻率，可唔可以產生另外一個駐波咧？而家我哋加大到24、25。
I double the frequency now.
咦，反而細咗好多喎。嗰個 pattern 咧都冇。
Now when the frequency does not match the standing wave
先
frequency,
至會產生另一個駐
the
波咧。
disturbance is very
不如我
small.
試下1倍啊！頭先
Now we double the
21.5
frequency.
乘2咧，就即係43赫茲。
This is doubling the frequency.
大家睇到啦，我而家咧嗰個頻率咧大概就係43赫茲度。咁你見到咧又產生另一個駐波咯喎。呢度咧今次唔係波幅啦，而係產生一個波折。呢兩邊有兩個波幅，咁咧即係話兩個波幅震得最緊要嘅，3個波折震得最少嘅。咁第三個駐波，大家估唔估到頻率係幾多咧？冇錯啦，就係21.5乘3，即係64.5啦。嗱，你見到中間嗰度咧，嗰啲頻率唔啱嘅時候咧，佢冇乜震動嗰條線。但係當佢去到接近個共振嘅時候咧，你見到咧嗰個駐波咧就好靚啦。嗱，今次咧大家估到啦，我有3個波幅，波折咧有1、2、3、4個波折。咁下一個係幾多咧？就係21.5乘4，即係86啦。咁我而家又加大個頻率咯喎。嗱，呢個咧雖然個振幅比較少啲，但係大家都可以見到嘅。1、2、3、4，四度震得最大嘅地方咧就係波幅啦。波折咧呢度1、2、3、4、5個波折。咁大家可以想象啦，如果一路咁樣上去嘅話咧，就會越嚟越多波幅同埋越嚟越多波折嘅喎。駐波有一樣好特別嘅地方咧，就係唔係所有嘅頻率都可以產生駐波嘅。要當嗰啲頻率咧係啱啱等於呢一個基頻，即係最低嗰個共振頻率嘅整數倍嘅時候咧，我哋先至可以產生駐波嘅啫。好啦，咁我哋睇下咧，我哋頭先見到嗰幾個駐波。咁咧嗱，最上面嗰個咧其實就係好簡單啦，就係一個波幅嘅啫。咁咧，你見到一個波幅咧，其實係半個波長嚟嘅。咁所以即係話一個波長咧，就啱啱等於條繩嘅長度嘅2倍，lambda 等於2個 L。第二個咧，你見到兩個波幅喎，啱啱係一個完整嘅波，咁所以咧個波長 lambda 咧就啱啱等於1個 L，即係繩嘅長度啦。第三個咧有3個波幅，嗰個波長 lambda 咧就等於2/3個 L。第四個有4個波幅，咁個 lambda 咧就等於 L 除2。嗱，其實咧，我哋可以將呢啲情況咧歸結為一條好簡單嘅公式嘅，就係個波長 lambda 咧就等於2倍嗰條繩嘅長度2L，跟住咧除翻 n 咧係一個整數1、2、3、4，咁最簡單個情況就係1啦，跟住2啦，跟住3，跟住4咁落去。嗱，如果我哋將呢條公式代翻入去我哋個波動方程，即係話個 F 頻率等於 v 波速除以 lambda， 即係嗰個波長。咁咧，我哋就會得到咧，其實個頻率咧係咩咧？呢個係駐波嘅頻率，係等於一個整數 n 乘翻一個基頻。
The frequency of the standing wave is equal to integer n multiplied by the fundamental frequency f naught。
我哋頭先所有嘅頻率咧，都係呢一個基頻嘅整數倍啦。
Okay, so that's very clear, right? Now let's proceed to a more difficult situation now. We are talking about a standing wave in a tube now. We talk about musical sound. Now, what is so special about musical sound is that we will show it like this. Is that it is a longitudinal wave, and there are actually two kinds of musical instrument that helps you to make musical sound. The first type is called a string instrument, and as its name suggests, is caused by vibrating string. So the vibrating string form a standing wave which is camped at the string is camped at both ends, so you form a standing wave, right? And the standing wave on the string vibrates the surrounding air, and so that gives rise to a musical sound, okay, with different frequency. And there's also another kind of instrument called pipe instrument or wind instrument. Essentially, it's a tube, and inside the tube you set up a standing sound wave. You vibrate, you blow it, or you blow when you blow it. It's set up, you set up vibration, and there's a standing sound wave inside the tube. And by controlling the length of the vibrating length by pressing on the hole of the tubes, you can adjust the frequency. You can adjust the frequency. You can adjust the length of the vibrating air column, and so you can adjust the frequency. Okay, so we are going to study the pipe instrument. We already have discussed a bit about the string, and now we are going to study the pipe. Now the string instrument is the following, right? We already have derived it before, and in terms of n, I can write this is a string camped at both ends, and so these are the normal modes, the standing wave that exists on the string, right? And in terms of the frequency, in terms of n, the frequency and the wave number can be written as with this form. Okay, the frequency, the angular frequency is n pi v over L, while the wave number is n pi over L. Okay, they both are proportional to the integer n. So with different n, you got different modes. Okay, so this is the frequency, the angular frequency, and if you like, you can express also in terms of the linear frequency, which is more intuitive. The linear frequency is omega divided by 2 pi. And so you now get rid of the pi, and you get nv over 2L. So this is the integer multiple of a fundamental frequency. The fundamental frequency is v over 2L. The fundamental frequency is the lowest frequency possible for a standing wave to form on the string is v over 2L. And all others, the higher frequency modes have frequency which are integral multiple of the fundamental frequency. Now, this we have shown in the video we have just seen, right? In order to form the higher frequency mode, you have to apply the frequency, vibrated string with a frequency that is equal to the integral multiple of the fundamental frequency v over 2L. Okay, now what we can see from this equation is the following. The frequency of the fundamental frequency of vibration determine the pitch. The pitch is essentially the frequency, the basic frequency of the musical sound. Okay, and it's dependent on the fundamental mode, because when the string vibrates, the fundamental mode always dominates over the higher order harmonics. Now there may be several vibration mode simultaneously existing on the string, but the fundamental modes always vibrate with the greatest amplitude, and so it dominates over the other what we call harmonics. The harmonics are the higher frequency mode, and the fundamental frequency mode will dominate over the higher harmonics. And so when you vibrate the string, you hear a sound which is essentially has a frequency equal to the fundamental frequency, that is v over 2L. Okay, so this is called the fundamental frequency. Okay, now a word of warning is that we state that the fundamental frequency is v over 2L, but v here is not the speed of sound. When we discuss about sound wave, we use the symbol to denote the speed of sound. But here, v is actually not the speed of sound. It is the speed of the wave on the string, because we are talking about standing wave on the string. So v here refers to the velocity of the waves on the string, but not in air. Okay. It is a string that vibrates the surrounding air to give you a sound. But the velocity that the frequency we are referring here refers to the speed of the wave on the string, but not the sound wave. Okay, so you must be careful. Now, so the pitch, as we say, the pitch is determined of a musical note. For example, do, re, mi, fa, sol, la, si, do is determined by the fundamental frequency. So it is this vibration that dominates over the others. Okay, so now if you analyze the musical sound using a CRO, for example, using an oscilloscope, you will see this kind of wave pattern. You can see essentially it is a sound wave. It is a what? It is a sinusoidal wave. It looks like a sinusoidal wave. Okay, so the fundamental frequency is determined by this period. Okay, the period of a sound wave. But you can see on the top of a sound of a sinusoidal wave, you have some up and down. The sine wave is not moved now, but you have some up and down tiny vibration, and those vibrations come from the higher frequency. It comes from the harmonics. What we call harmonics is a high frequency mode. So the higher frequency mode affect the total so-called quality of the sound. So the quality of a musical is actually determined by the numbers and amplitude of the harmonic excited, the high frequency mode. That modify the fundamental frequency vibration. Okay, so that explains why different kinds of musical instruments have different quality of sound. The quality of sound refers to the effect of the high frequency harmonics. So when you see a guitar and a violin, they both play a sound, for example, do. They have the same fundamental frequency. They have the middle C, for example, you play the middle C, they have the same fundamental frequency. But the violin middle C sounds very different from a guitar middle C, although they are both do, but they sound quite differently. It's because of the difference in the harmonics. So the quality of the sounds are different for different musical instrument, even though the fundamental frequency, the pitch is the same. Okay, now you can play around with your with this instrument if you have one. Now, for example, I sound R, you can see the waveform is like this. If I sound E, then you see you have a rather a waveform that is rather similar to a sinusoidal wave of a single frequency, although there are tiny vibration due to the higher frequency mode. You can see it, right? If you see O, then you sound something like this. They always have a fundamental frequency and is modulated by some higher order frequency. Okay. Now we talk about the pipe instrument. Okay. Now the pipe instrument, the simplest pipe instrument is a pipe. It's a long pipe that is open at both ends. Now these two ends are not closed, because if you close both ends, you cannot excite the vibration inside, right? So you must open at least one end in order to set up the vibration. Now we open both ends. We leave both ends open. Now when both ends are open, when a standing wave is formed inside, the vibration of the air molecule will be maximum. There will be a maximum in the displacement of the air molecule, or a knock or anti-knock, okay, anti-knock of the displacement at the ends. Now, why is it so? You may wonder, why is the displacement of the air molecule maximum at the open end? Now you can understand like this. There's a pressure variation, right, inside the tube. When the tube meets with the surrounding air, when the tube is open at both ends, and when this end joined with the atmosphere, when it meets the atmosphere, the pressure here, the pressure at the two ends, will become equal to the atmospheric pressure. That means the pressure here at the both ends is the same as the atmospheric pressure, right? So if the standing waveform, the two ends must be a knock for the pressure. So the pressure change there must be 0, right? So there's a knock at the two ends for the pressure waves. Is that okay? But the pressure waves, but a zero in the disturbance for the pressure corresponding to a maximum vibration in the displacement. If you don't remember, I helped you with this slide. Whenever you have a zero disturbance, you have a zero disturbance in the pressure, like here, it always corresponding to what? To a maximum or minimum, the largest displacement of the N molecule. The zero pressure, the zero disturbance in the pressure correspond to the largest amplitude, largest vibration in the N molecule. Because they are pi over 2 our phase. The two sine wave, the pressure waves and the displacement wave, they are pi over 2 our phase. Okay, so that's why it's zero in the pressure corresponding to a maximum vibration in the N molecule. Now, so with this understanding, we would like to construct a standing wave pattern for the displacement wave now. So the first harmonic of the displacement wave, that is the fundamental frequency. Now, the first harmonic is just the fundamental frequency. The fundamental frequency waves is just like this. The disturbance, now this is the disturbance, the displacement wave for the N molecule. The displacement is the U is maximum at both ends. The U is maximum at both ends. And there's a nook in the middle. It's different from a string. When you have a string, the displacement at both ends are zero, right? But now the reverse happened. For a tube that is open at both ends, the disturbance of the N molecule at the two ends are maximum. These are the anti-nooks for the air displacement. Okay, and so for the fundamental, the lowest frequency mode, you have a nook in the middle. You have nook in the middle. How about the high order modes? The high order modes consists of something like this. You have half wavelength more for the N equal to 2 modes. Okay, you have still one more half wavelength for N equal to 3 modes, and for N equal to 4 modes, you have three half wavelength in the middle. Now that's corresponding to this formula again. Okay. Now, although now you have a different boundary condition, you still have this formula. If you check this, you will find that for the zero disturbance, the wavelength is actually half of the length of the string. Now, because when the maximum goes to the minimum, it is half of the wavelength, right? So the wavelength now is half the length of the string. And for this situation, the wavelength is equal to the length of the string. Is that right? It is a full wave, right? A full wave. From maximum to minimum to maximum, that is a full wave. So the lambda is equal to L. And for this situation, it is 1.5 wavelength. So lambda is equal to 2L over 3. And for this situation, you have 2 wavelength now. So lambda is equal to L over 2. Okay, and when you summarize all this situation, it becomes this formula. Lambda is equal to 2L over N. And if you convert this into the frequency, if you apply the formula F is equal to V over lambda, you got the frequency equal to NV over 2L. So in terms of the wavelength and the frequency, it's just the same as a vibrating string. Okay, you still have lambda equal to 2L over N, and you still have the frequency equal to N multiplied by V over 2L. Okay. Now we have some modification. We imagine the tube is open at one end and closed at the other. Okay, so you imagine the tube like this. It is closed at one end and open at the other end. So how would the modification? How would it modify the frequency? We look at this. Okay. Now we draw the picture to make it more intuitive. Instead of starting with the mathematical derivation, we draw a picture. If I close it at this end, at the left end, then the air because the air disturbance is parallel to the length of the tube, right? So if I close the tube, the displacement must be 0, right? The displacement must be 0. So there will be a knock. There will be a knock in the displacement. The molecule here could not move. So the disturbance must be 0 at the closed end. However, on the open end, the pressure is equal to the atmospheric pressure. So the pressure disturbance is 0. And the pressure disturbance is 0 corresponding to a maximum vibration, a maximum amplitude for the displacement. So that's why there's a maximum here on the right hand, because it's open. Okay. Now, so what would be the fundamental here? The fundamental here, you can see it is only a quarter of a wavelength, because I have 0 to a maximum. This from 0 to a maximum is only a quarter of a wavelength. So that means the wavelength is 4 times the length of the tube. Because in the length of the tube, you only have a quarter of a wavelength. And that means the full wavelength is 4 times the length of the tube. Is that right? And how about the second harmonic? Well, for the second harmonic, you have another half of a wavelength here, right? So the length of the tube is now equal to 3/4 of the length of the tube. The wavelength is now the length of the tube is equal to 3/4 of a wavelength. Okay, so that is the relation. And for n equal to 5, and for this mole, you have two more half wavelength here. So you can see in this figure, it is 1 wavelength and a quarter, 1 1/4 wavelength. So that means the length of the tube is equal to 5/4 wavelength. Okay, and for this figure, you can see the length of the tube is equal to 1 3/4 of a wavelength. Okay, so that means the wavelength is equal to 4L/7. Okay, and so on and so forth. Now this can be summarized by using this formula. Instead of 2L/n, you now have 4L/n, but with n equal to odd integer. Now you can see from this, when n is equal to 1, that gives you lambda equal to 4L. When n is equal to 2, when it's equal to 3, because we only count the odd integer. When n is equal to 3, you got lambda 4L/3, which is this situation. When n is equal to 5, you get this situation. When n is equal to 7, you got this situation. Okay, so that's how we relate the wavelength with the length of the string for a tube that is open at one end and closed at the other. Okay. Now let's go more difficult. Let's handle the mathematics now. Now here we only show you the picture and derive this relation, right? Now we go to the more difficult mathematics. We want to write down the waves, the wave pattern inside the tube. For simplicity, we only focus ourselves with a wave with a tube that's open at both ends. And in order to match the boundary condition, because we are writing the U, and U is a maximum, is an antinode at the 2 ends. So in order to match the boundary condition, we choose a standing wave solution with a cosine. Because we know the cosine, when x is 0, cosine is a maximum. And we can also make the other end to be also another maximum, right? With the cosine. So the cosine is a suitable function to fit the boundary condition. So that's why for the standing wave solution, we choose a cosine instead of sine. Now, when we talk about the vibrating string camped at both ends, we use the sine kx, right? Because we want to match the boundary condition that at the both ends, the disturbance is 0. Okay? But now we want to match the boundary condition in which the disturbance is maximum at both ends. So instead of using the sine, we use the cosine function. We use cosine kx. Okay? Now, so the boundary condition can be matched by the following. We need at x equal to 0, the disturbance is maximum. But this must be true because cosine K0 is 1, which is the maximum value for the cosine. So it must be satisfied. And on the other end, if I substitute x equal to L, that should be a maximum on the other end. And so in order to make that n a maximum disturbance, cosine KL must either be equal to +1 or -1 because it's the largest possible magnitude for the cosine function. And because it's the maximum, we want to make it cosine KL equal to + or -1. And that again, corresponding to the situation where KL is equal to n pi. When KL is equal, cosine KL is equal to +1, then the angle is equal to 0, right? When cosine KL is equal to -1, the angle is equal to pi. Okay, so that means KL is equal to n pi, where n is 0, 1, 2, 3, 4. I should omit the 0 because it just doesn't make sense for that. It should be 1, 2, 3, 4. Okay, n is equal to 1, 2, 3, 4. And that will corresponding to K equal to n pi over L. N pi over L. Is that right? Where there's a typo here. Please cross out the O, the 0. That corresponds to K equal to n pi over L or lambda equal to 2L over n as before. So that's why we have the same formula. Okay. The boundary condition is now different. But after taking all the boundary condition in consideration, we arrive at the same formula as the right-beating string. And the frequency is, of course, given by kV, and that is equal to n pi v over L. Okay. This situation we have discussed before, right? Now, this is a displacement wave only. This is U. U is the displacement. We now derive the pressure waves. The pressure wave is equal to minus the bulk modulus multiplied by the spatial derivative of U. So that amounts to a straightforward differentiation of U with respect to X. So when you have U, you just substitute the U into this equation and find the P. Okay. The differentiation in X acts on this factor, act on the factor cosine Kx. And that becomes minus sine Kx. And the minus sign cancel with the minus sign in front. So that becomes a plus sign. And the chain rule will give you an additional factor of K. Okay. And by some manipulation, we know the wave speed is equal to square root B over rho naught. So, and K can be expressed in terms of omega and V. K is just equal to omega over V. And by these two replacement, we arrive at the wave, the amplitude for the pressure as rho naught V omega U naught. That's a simple algebra. We just follow the simple rules. And so this is the pressure waves. Now you can see immediately, you can see the pressure wave depending on the sine function now, sine Kx. So at x equal to 0, the pressure wave is a knock. Okay, so there's knock here. This is the pressure wave. And for when x is equal to L, sine KL is also 0. Because sine KL, because K is n pi over L, so when I multiply by L, it becomes sine n pi. That is 0. So that means the boundary condition at the both ends are satisfied. Okay, so for the pressure wave, there are knocks at the both ends. Okay, for the displacement wave, the n molecule are based at maximum on both ends. So I have a cosine function here, but for the pressure wave, the disturbance is 0 at both ends. So I got the sine function as sine Kx for the spatial dependence. Okay. Now in your homework, you are given another example. We want to work with this situation. Okay, we have one end closed and the other end maximum. Now you are required to match that with a sine Kx function. This end when for U, when this end is U is 0 at this end, you can match it with a sine function because sine is 0 at when x is equal to 0. But for the other end, you need a maximum. And the maximum for a sine function, if you have a maximum for a sine function, that means sine KL should be equal to +1 or -1. And that gives you KL instead of equal to pi, you now have would equal to pi over 2 or 3 pi over 2, right? And that gives you another series for the boundary condition. Okay, so try to work it out yourself. For the homework, we only would like to find the fundamental frequency. So you only need to set, in fact, you only need to set KL equal to n pi over 2, where n is equal to 1. Okay, so KL is equal to pi over 2 for the maximum on the right end. Okay. Now, I would like to talk a little bit about how we speak. Now, there's a misconception about speaking. People always thought that we can pronounce different, we can produce different sound because our vocal fold or vocal cords oscillate with different frequency. Okay, we can control our vocal cords such that it produces different frequency. Now, the fact is we cannot control our vocal cords. Our vocal cords always vibrate like this. It's due to the air rushing into the cord and setting it into vibration. And the vocal cord actually always vibrate with the same series of frequency. But the frequency is not a single frequency. It consists of a series of different modes of vibration. So it's a multiple frequency vibration. It produces all kinds of frequency that when you speak, it consists of all kinds of frequency that your company can produce. But how we actually pronounce a certain frequency? But because when we speak, we can produce different frequency to distinguish one word from the other, right? So there must be a way for us to produce that sound, a particular frequency vibration. Now, the mechanism is rather tricky. The mechanism actually consists of depends on resonance. It happens that our oral cavity and nasal cavity, they are in a shape that we can control. When we say different, we pronounce different words, we control our oral cavity. We control the shape of our oral cavity. Okay, and we also control whether our mouth is open or closed. When pronouncing some words, we open our mouths, and pronouncing another words, we close our mouth. And that changed the resonant frequency inside. Because the boundary condition depends on whether we close or open our mouth. So this are the situation. When we open our mouth is like this, is a maximum for the U. When we close our mouth, it will be a look for the displacement. So that affects the resonance frequency inside. Okay, so by changing the shape, the length of the oral cavity by using your tongue, you change the shape of the oral cavity, and using your mouth, the shape of your mouth, and close it or open it, you resonate with different sound, different frequency that is produced by the vocal cord. You amplify certain frequency by resonance. By adjusting the resonance here, resonant cavity here, you amplify certain frequency while suppressing the other frequency. Okay, so that's how you speak, you produce different sound. Okay. Now this is main end. Okay. Now let's see what happens when main end inhales some helium. Let's see what happens when main end inhales some helium. This is an interesting video. I share it.
中大嘅同學仔，你哋好，係時候要表演俾你睇啦。Only you can take me 吹世嘅，你中大。
藍沙妖精鬼怪，唔好驚，嗌聲嗌下對聲，要全力對開都有問題就揾湯博士咯。拜拜。
That's another video with Gaki.
我想去旅行啊！我哋需要旅行社嘅 sponsor。
旅行揾關鍵，招式出色試食超級超值，耶！
冇啦，
去揾
同關鍵一樣冇啦，
冇啦，冇啦。
So why would when we have some helium, why would the sound pitch become higher, the frequency become higher? You may not understand why. The reason is the following. You look at the formula. V is equal to F lambda, right? This is a standard wave equation. Now, but the resonance wavelength, the resonant wavelength is actually determined by the shape of her mouth, right? When he shaped the mouth in a certain way, when she speak, he should shape the mouth, her mouth in a certain manner. You close the mouth, or use the shape of the tongue in a certain way, and so that determines the wavelength of the vibration, right? But when she inhales some helium, in helium, the density is less than air. So by the formula V equal to square root B over rho, when the density is less, the wave speed becomes higher, right? If you look at this formula, if lambda is fixed by the shape of the mouth, the resonant wavelength is fixed by the shape of the mouth. And when we increase, when we increase due to the inhalation of the helium, okay, the frequency F will also increase. So that's why he sounds with a higher pitch. Okay, so that is again a phenomenon for resonance. Okay. Now we also can talk about a little bit about sound intensity. The intensity of a sound wave determines its loudness, and the intensity is equal to the power per unit area. Okay. If you have a sound source, and the sound source gives out sound wave in different directions, presumably evenly in all directions, for example, and then the loudness of a sound can be obtained by dividing the power produced by the sound wave divided by the area of the reception at a certain distance from the source. So the power per unit area gives you the intensity, which is the loudness, essentially the loudness of the sound you hear. Okay, and the units for the intensity of sound, that is the loudness, is power per unit area. So it's watt per meter square. Okay. Now, if I consider an isotropic sound source, that means the sound is now spreading out evenly in all directions. Now that almost never happens because sound source always have a preferential direction. But suppose it happens now for simplicity of our discussion. Suppose you have an isotropic sound source which produces sound wave evenly in all directions from a source of power PS. This is a total power produced by the source. And if the power now distribute to a large sphere of radius r, then the surface area of the sphere is 4 pi r squared, right? Because it's spread out to a large surface area. And by our definition, the loudness is the power, the total power, divided by the area. So it's PS divided by 4 pi r squared. But if the power is a constant, P is a property for the source, it is a constant. Then if I go to a farther distance, the R will increase. The loudness of the sound will decrease as 1 over R squared. So that is the kind of inverse square law force. if I increase my distance from the source, if I double the distance from the source, the loudness of the sound will decrease by 4 times. Okay, because of the inverse square law of force, because it's the loudness decrease with 1/r square. Okay, and the loudness of a sound is actually measured by decibel. Now, air disturbance in air, displacement in air that human ears can hear have a very wide range. And for the sound that human ear can barely hear, the displacement wave may be as small as 10 to the power minus 11. That is on the atomic scale. Okay, this is about the size of an atom. The air molecule actually vibrates very tiny way, and that is the minimum amplitude sound that human ears can barely hear. And the loudest sound that can tolerate have an amplitude of 10 to the power minus 5 meter. This refers to the displacement wave u, the amplitude of the displacement wave u. Now this value we actually have estimated before in our classwork, right? So there's an amazing sensitivity. There's an enormous range. The range is from 10 to the power minus 11 to 10 to the power minus 5, which is 6 order of magnitude. So we do not use a linear scale for that because the range is so wide. Instead, we measure the sound intensity not by a linear scale, but by a log scale. A log scale allows us to accommodate a wide range of frequency loudness variation. So we measure that using a decibel scale, which is a log scale. And we define a sound level by beta. Beta is equal to 10 decibel multiplied by log. This logarithm is of the base 10, not of the base e. This is the logarithm of the base 10. Logarithm I over I naught. I is the intensity of sound you want to measure, and I naught refers to the standard reference intensity. I naught is actually the lowest intensity sound that human ear can barely hear. Okay, and that corresponding to an intensity of 10 to the power minus 12, which is very small, watt per meter square. Now, so when I is equal to I naught, that's a hearing threshold. You just can hear a sound. This is the threshold below which you cannot hear. And that corresponds to 0 decibel. And this, because this is a log scale, if you check it, if you have a 10 decibel increase in sound wave, the intensity for every 10 increase in 10 decibel, the intensity increased by 10 times. Okay, now this easy to calculate. For example, you have intensity I equal to if compared to sound, if your I is 10 times I naught, then corresponding to log 10, right? Multiplied by 10 decibel. Okay, and you can, it's a base log 10. It's log 10, not log E. Log E, we use a ln for symbol. Now we have a log with base 10. Okay. Now I let you calculate yourself. Suppose you have a two sound. I leave it to you for an exercise. Suppose you have two sound. The first sound is beta 1, corresponding to what? Corresponding to log I1 over I naught. The beta 2 is another sound, corresponding to log I2 over I naught. So they have different intensity, right? So what are the difference between the two? If I2 is louder, then beta 2 minus beta 1 is what? The difference between the loudest, the sound intensity is what? Is equal to 10 decibel, right? Log this two, when this two subtract, it becomes I2 minus I1. The I naught cancel. Okay. So if, say, for example, I2 is equal to 10 times I1. Okay, then this is what? Equal to what? This factor is equal to 1 because log 10 is 1. So the difference is equal to 10 decibel. Equal to 10 decibel. That means 10 decibel corresponding to an intensity increase by 10 times. Okay, so a difference in 10 decibel corresponding to an increase in intensity for 10 times. Okay, so it's a multiple by 10. Okay, it's not simply adding up the intensity, but the log scale. Okay, so for example, if you have a 40 decibel, that means the intensity is 10,000 times of the threshold of hearing. Okay, so you understand this scale. We better not have a. We better finish it before having a short break. Now we have a very brief discussion on the solid in of a sound wave in a solid. Okay, this is a very brief discussion, not very important, but we still want to have a complete discussion on both the sound in gas or in liquid and solid. Now we go back to the wave speed on the string. For string, for vibrating string, this is a transverse wave. It's not a sound wave. A transverse wave on the string, we have the velocity given by square root tau over mu, where tau is the tension, right? The elastic property is the tension, and mu is the mass per unit length of the string, and that is the density, essentially the density. The density is a mass per unit length or per unit area, per unit volume, right? So mu is actually the linear density, the mass per unit length. Now for a sound wave in air, you have this, right? The bulk modulus derived by density square root. The bulk modulus somehow give you the elastic property of the medium. If the bulk modulus is large, that means the gas is difficult to compress. You need a large pressure to compress the gas just by a little bit. That is meant by the bulk modulus. So again, the bulk modulus represents the elastic property of the medium. Okay, it sounds like the tension. Okay, it plays a role of a tension in the string. They are very similar concept. And on the denominator, you see that you have a density. But now for air, you have the density of air, the mass per unit volume. Okay, but it's still the density. And there's a similarity between the two. And in fact, for all kinds of mechanical waves, you have this property. Is that the wave speed is essentially the square root of the elastic property divided by the mass density. The elastic property corresponding to, for example, the tension, the pressure, which characterize what happens when the gas or the medium get compressed or rarefied. Okay, this is the response when the medium is get compressed or rarefied, and that's we call the elastic property. And this is characterized by either the tension in the string or the bulk modulus for air column. And the inertia is a mass density. Okay, either characterized by the linear density for string or the volume density for air. Okay. So we want to ask, what will be the equivalent in a solid? If we extend our discussion to a solid, what will be this expression? We want to find the expression for sound wave for a solid. So what will be that? Now we consider a rod and metal rod under tension. Suppose you have a very thin, you may consider a very thin wire, actually, a thin wire of metal, which is a solid, of course. And you have a very small cross-sectional area A, and the natural length of the wire is L. This is an unstretched length. Okay, when it's not under tension, the length of the wire is L. Okay, suppose the wire is now under tension. The tension force is L. Okay, I apply a tension force F to the wire. This is the apply the force, and because of you stretch it, There's some elastic property in it. So it will result in some extension. And extension I call delta L. That is a small change in length due to the stretching force. Okay. Now, so what we define the material property is this. We define the stress. The stress is essentially the pressure. But for pressure, we actually consists of the pressing force. We press the object together, right? That's called pressure. But now we have stretching force. So the stretching force is normally referred to as stress. That's a stretching pressure. The stress is the force per unit area and is defined as sigma. Sigma is the force per unit area due to the stretching force. Okay. Now you can see essentially this is a pressure, but it's in the reverse direction. For the pressure, we press on it, but now we're stretching it. Okay. So again, it is a pressure, but refer to the stretching force. Okay. The force divided by area. And we denote the stress by the symbol sigma. What is a strain? The strain is a fractional change in length. It is a change in length divided by original length. So I denote the strain by the strain by E. That is a symbol for the strain. Okay. Now experimentally, we find the following fact. We find that for a wide range of stress, the stress is proportional to strain. And that is a constant for a given material. That means if you choose a given material, for example, a steel or aluminum, for example, you do the experiment, you plot a graph of the stress against strain, you find that it would be a straight line. They would be proportional to each other. The stress is proportional to strain. If you apply a larger stress, you will find that the wire will have a larger fractional change in length. Okay, so stress is proportional to strain, and that ratio is constant for a given material. Okay, and how do we define that constant? That constant is called the Buck modulus, the Young's modulus. Okay, sigma over E, the stress divided by the strain, is called the Buck modulus. Young's modulus, sorry, Young's modulus. And I denote the Young's modulus by E. Okay, so if I write in terms of F and L, I have F over A equal to a constant E multiplied by delta L for L. And again, a larger E means a larger stress is needed to produce a given fractional change in length. You see from this formula, if E is larger, right, that means I need a larger stress to produce a given change in length, a fractional change in length. So the material is called less ductile. It cannot be stretched easily. Ductile means how easy you can deform the material by producing a stretching force. Okay, if the material gets easily extended by the stretching force, that means the material is very ductile. But a larger E means the material is less ductile. You need a large stress to produce a small change in length. So a large E means a less ductile material. Okay. Now these are the typical value for the Young's modulus. For example, steel, aluminum, concrete, bone, polystyrene. You see for steel, the metal is actually a ductile material. It is quite easy for metal to extend under stretching force. Okay, so you see for materials like steel and aluminum, the Young's modulus is actually quite large compared with other non-metal. You see, concrete is very difficult to elongate. Okay, and but even for steel, the value for the Young's modulus is very large. You know the unit. The unit is 10 to the power 9 Pascal, which is a very large value. It's a gigapascal. Now you can see from this formula that the unit for the Young's modulus is the pressure. delta L over L, the length divided by length, does not carry a dimension. So the dimension for E is actually equal to the dimension for the stress. Dimension for the stress is the pressure. And the unit for pressure is Pascal. So you have a Pascal here as a unit for the Young's modulus. Okay. Now we derive the expression for what happens when the metal gets compressed. Okay. Now we know that for metal, for solid, you have the stress equal to F over A, and now by previous discussion, F over A is proportional to delta L over L, and the proportional constant is the bulk modulus, the Young's modulus E. Okay. Now if I multiply on the numerator and the denominator by the cross-sectional area A multiplied by delta L is a change in volume V1. And A multiplied by L is original volume V0. So it becomes equal to the stress. The stress becomes equal to the constant E, the Young modulus, multiplied by the fractional change in volume, V1 over V0. Now that can be compared with this expression for a gas compression. For a gas compression, we arrive at this formula. The change in pressure being proportional to a fractional change in volume, and the proportional constant is the bulk modulus. Now we have a very similar formula, but the proportional constant is the Young's modulus for a solid. And that's another difference. Because in here, we consider a compression. So there's a negative sign between the volume contraction and the pressure change. When the gas is compressed, when V1 is negative, the pressure is positive. But in this formula, we have a stretching force. When the stretching force becomes larger, the volume change is larger. So there's a plus sign. But the idea is similar, actually. And we expect that when we compress a solid, there would be a minus sign here. Okay. So the Young modulus in solid roughly corresponds to the bulk modulus in a gas. So we expect the sound speed we are approximately given by this formula. Instead of using the bulk modulus for gas, we can use the Young modulus for air, for the solid. Okay. So V is proportional to square root E over rho naught. Now, but it happens that this formula is roughly correct for longitudinal wave, because in a solid, we have two kinds of, actually we have to have two kinds or more than two kinds of sound wave. The first kind of sound wave is a longitudinal sound wave, just like air column. We vibrate the air column gets compressed and rarefied, and that is some kind of longitudinal wave that propagates forward. Okay, so this formula actually corresponds to a longitudinal wave. Okay, but there's also transverse wave in a solid. Sound can produce as a transverse wave inside a solid because there is a shear force between two layers of material. Okay, and that cannot be described by this formula. Okay, and also I actually confused the bulk modulus with the Young's modulus here. The reason is subtle because the solid actually gets compressed laterally. So the bulk modulus is actually not exactly the same as the Young's modulus. Okay, and so this formula is not strictly correct. But I do not want to go into a very detailed discussion with you about the difference. But this formula can give you an order of estimation of the velocity of sound in a solid. Okay, so now we ignore the difference between the shear, the transverse component. We don't consider that. We consider a longitudinal component, and with the elastic property described almost by the Young's modulus. Now, let's have a break for 5 minutes, and then we come back to discuss about the Doppler effect, and that is a